So today we are going to discuss about measurable sets. So we have already defined what is outer measure, and now we are going to define measurable sets. What is a measurable set or a Lebesgue measurable set? Okay, so for that we are going to use the previous results. So for example, if A is a subset of B, then outer measure of A is less than or equal to outer measure of B. And then also we are going to use countable sub-additive formula. That is, if EI is a sequence of measurable set or sequence of set, then their union outer measure of their union is less than or equal to sum of the measure of the individual set EI. So that we call it countable sub-additive formula. We are going to use that one also in proving some of the important results in this lecture. Okay, so now first let us define what do you mean by a measurable set. So measurable set, a set E is said to be measurable. So a set E is said to be measurable or Lebesgue measurable if for each set A we have this equality, that is outer measure of A is equal to outer measure of A intersection E plus outer measure A intersection E complement. So we are going to show the measurability of the set E. Then we have to show this equality for any set A. We are going to show this equality M star A is equal to M star A intersection E plus M star A intersection E complement for any set A. So if this equality holds true for any set A, then we are going to say that this set E is measurable or Lebesgue outer measurable. So then in order to show the equality or measurability of a set E, we need to show this inequality. If these two inequality holds true, then this equality is okay. All right. So these two inequality we are going to show, and then we will be getting this equality that for every set A. So since outer measure is sub-additive, here we are going to use the countable sub-additive formula or result. So M star, M star A, the set A can be written as a union of this set A intersection E union A intersection E complement, because A can be written as in this form. Therefore, outer measure of A will be less than or equal to sum of the outer measure of A intersection E plus outer measure A intersection E complement. So this is always true for any set A. So therefore, the other inequality it is sufficient to prove this inequality only. In order to show that E is measurable, we have to show M star A is greater than or equal to M star A intersection E plus M star A intersection E complement for any set A. So let us see some simple example. So M star E, suppose M star E is equal to 0, then we are going to show that E is measurable, right? M star E is equal to 0, then we are going to show that E is measurable. So let us see. For any set A, we have this one. This inequality is always true. For any set A intersection E is always a subset of E. Also, A intersection E complement is a subset of A. These are true for any set A. So, see, this one is subset of this one. So, outer measure of this one will be less than or equal to outer measure of this one. But outer measure of E is equal to 0. But this cannot be a negative number, therefore outer measure of A intersection E must be 0 also. So that is what I am writing here, outer measure of A intersection E is equal to 0, right? So again, A intersection E complement is a subset of A, therefore outer measure of A intersection E complement will be a subset of outer measure of A. So from this we get outer measure of A intersection E plus outer measure of A intersection E complement is less than or equal to outer measure of A. So this is true for any subset A. Therefore, we have this equality, outer measure of A intersection E plus outer measure of A intersection E complement is exactly equal to outer measure of A for any set A, and hence E is measurable. Alright, so this is a very simple example. Yeah, now let us prove a very important result. The class M of measurable set is a sigma algebra. So what we are going to show is that the collection of measurable set is a sigma algebra. That means suppose the collection of sigma measurable set is denoted by M, then if you take any member from M, you take complement, the complement is also in M, right? If you take a sequence of set in M, you take the union is also in M. That is what we are going to show, and then M will be a sigma algebra. So let us see. So for any set A, we have, A intersection A is equal to A intersection R. This is obvious, and A intersection R complement. So what is the R complement? Is phi. So it is phi. Therefore, M star A is equal to M star A intersection R. Alright, and M star A intersection R complement is equal to 0. So that is why you can write like this: M star A is equal to M star A intersection R plus M star A intersection R complement. Because this part is 0, you can add up here. So you have the equality. It shows that R is a member of M. R is measurable. It shows that R is measurable. That means R is a member of M. Alright. So next, if E is measurable, if E is measurable, that is E is a member of M. We have M star A is equal to M star A intersection E plus M star A intersection E complement for any set A. That is M star A is equal to M star A intersection E complement plus M star A intersection E. From the symmetry, you can conclude that EC is also measurable, and therefore EC is a member of M. So it shows that M is closed under the formation of complement. Now it remains to be shown that if this one is a sequence of sets in M, then their union is also in M. Let the union be denoted by capital E. So we are going to show that E is in here, M. So since E1 is measurable, okay, for any set A, we have this equality: M star A is equal to M star A intersection E1 plus M star A intersection E1 complement. Let it be equation number 1. So also E2 is measurable. Since E2 is measurable for any set A, this equality also true in case of E2 also. Since it is for any set A, you can deliberately take A intersection E1 as set A. So therefore for the set, A intersection E1 complement. So for the set A intersection E1 complement, we must have M star A intersection E1 complement is exactly equal to M star A intersection E1 complement intersection E2 plus M star A intersection E1 complement intersection E2 complement. So if we put this quantity here, so we will get the following equality. So we have M star A is equal to M star A intersection E1 plus M star A intersection E2 intersection E1 complement plus M star A intersection E1 complement intersection E2 complement. Let it be equation number 2. So continuing in this way, we obtain for any n greater than or equal to 2, M star A is equal to summation M star A intersection E1 plus summation I running from 2 to n M star A intersection EI intersection j less than I EJ complement. Alright, so M star A intersection j running from 1 to n EC. Alright, so what we are doing is that we are applying the same result here we are getting from E2. This is coming from E2 measurability. So like that, from the condition that E3 is measurable, so using this set you can find another equality. So like that, so that process you continue. Alright, so that means for any n greater than or equal to 2, you have this equality: M star A is exactly equal to M star A intersection E1 plus summation I running from 2 to n M star A intersection EI intersection and intersection j less than I Ej complement plus m star A intersection and intersection j running from 1 to n Ej complement. So by using De Morgan's law, this can be converted in this form, that is A intersection union j running from 1 to n Ej complement is outside. Alright, bracket. So this one also, here intersection by using De Morgan's law, this will be union j less than I Ej complement is outside. So you can write like this. Alright, so then what happened? This is union j running from 1 to n, and this is union j running from 1 to infinity. So this one will be a subset of this one, but if you take complement, this one will be a subset of all of this one. Alright, so without complement, this one is a superset of this one. If you take complement, this one will be a subset of this one. So since this one is a superset of this one, outer measure of this one will be greater than or equal to outer measure of this one. That is why I am writing here greater than or equal to. Alright, and this is true for any n. For any n, if you take n 100, n is equal to 1000, 1 billion, 1 million, it is always true. This inequality always true. Suppose if n tends to infinity also, it is also true. So that is why I am writing here m star A will be greater than or equal to m star A intersection E1 plus, since it is true for any n, it is true when n tends to infinity also. That is why you can write I running from 2 to infinity m star A intersection EI intersection, then union j less than I Ej and complement, whole complement, plus and this one. Alright, so now let us simplify this term. Now let us simplify this term. Okay, it can be shown that m star A intersection E1 plus summation I running from 2 to infinity m star A intersection EI intersection union j running from 1 to less than I Ej complement is greater than or equal to m star A intersection union j running from 1 to infinity Ej. So let us simplify this result. Alright, so for that, so let us see, when n is equal to 2, n is equal to 2, so what do you get? When n is equal to 2, instead of infinity here, you get I running from 2 to 2. Alright, so then what do you get? This is, let us see, this one A intersection, when I is running from 2 to 2, then it will be A intersection E2. So this will be A intersection E2, and then so let us see, intersection union j is less than I. Alright, so then what do you write? A intersection E2, you get this one intersection, and then union j is less than 2 is a complement. So since j is less than 2, the only possibility is j is equal to 1. This is equal to A intersection E2, and then you have intersection, so this is E. So what is this one? This is equal to E1 complement. You have this one. Alright, so and then you have this one, A intersection E2 intersection E1 complement, and this is equal to A intersection E2 difference E1. You have this one. And suppose if you take union here, both sides, you take union A intersection E1. If you take union here, alright, what do you get? So then if you have to take union here also, you have to take union here also, and ultimately you have to take union here also, union A intersection E1. Alright, so this you can write like this, A E2 difference E1 and then the union E1. So you take out from E2 E1, and then again you take E1 union, that you exactly equal to A, this one here, intersection. So E1 union E2. So this you can write A intersection union I is running from 1 to 2 EI. You can write like this. That means this term is exactly equal to this term. Right? Therefore, outer measure of this one must be equal to outer measure of this one. Alright, that you have. That is for when I is equal to 2, n is equal to 2. Suppose if you take n is equal to, say, n is equal to 3, what do you get? In this one, instead of taking infinity, if you take infinity here 3, then I has to run from 2 to 3. So then what do you get? Let us see. So this will be, this will be union. Okay, A intersection E2. All right, and then intersection E1 complement, this one, then union. So A intersection E3, then intersection, then here E1 complement, intersection E2 complement. You will have this one. So, and then you have to take A intersection E1 union here. Alright, so we have already shown that from here to here it is equal to how much? This is equal to A intersection E1 union E2. That is, we have already shown that from here to here it is equal to A intersection union E1 union E2, and then you have to take union here. So from here, this one again, you can show that this is exactly equal to A, intersection E3, then you take out E1 union E2. So then again you can write like this, A intersection, so this one you can write like this, this one go inside. All right, so E1 union E2. All right, so union E3, you take out E1 union E2. So this one, after simplification, you can write that this is what? This is E1 union E2 union E3. So this is A intersection E1 union E2 union E3. You can write like this, and this you can simplify like this: A intersection union I running from 1 to 3 E1 intersection, EI union. You can write like this. So that means then if you take outer measure here, that should be exactly equal to outer measure here. All right, but this is union, this one union, this one union, this one. So since outer measure is countably subadditive, outer measure of this one plus outer measure of this one plus outer measure of this one will be greater than or equal to outer measure of this one. All right, so that is what I'm saying here. So yeah, this one, this can be simplified. All right, so then as n tends to infinity, here infinity will be there, the sum of this outer measure will be greater than this one. All right, when n is equal to 3, we have already proved that outer measure of this one will be greater than or equal to here, and here it will be 3. All right, for 2 also, for any n also it is true, and when n tends to infinity it is also true. So this term will be greater than or equal to this one. So using this fact, you can write like this. So this term from here to here can be replaced by this one and inequality goes. Okay, so this one, since this part is greater than this one, so this whole thing will be greater than this one. All right, and this remain as it is. All right, so this is what we wanted to prove. So the left hand side here is m star a. M star a is greater than this one, therefore this union is measurable. Okay, this union is measurable. This union, if you take it E, so A intersection E, and this one is A intersection E complement, that is less than or equal to m star a for any set A. That is what we wanted to show. So therefore m star a will be greater than or equal to m star a intersection this set plus m star a intersection complement of this set. All right, so it shows that m star a is exactly equal to m star a intersection union this one plus m star a intersection this one. So what does it say? So this set, the union is measurable. Since it is measurable, it is a member of this collection M. So it completes the proof that M is a sigma algebra, right? M is a sigma algebra. So next example, so that F is measurable and M star F symmetric difference G is equal to 0, then G is measurable. So what we are going to show that we are going to assume that F is measurable and M star F symmetric difference G is equal to 0, then we are going to show that G is measurable. All right, so we know that the symmetric difference is defined by this one, F difference G union G difference F. So and then from the equality, it is very clear that F difference G is a subset of F symmetric difference G, and G difference F is a subset of F symmetric difference G. Therefore, what you get? Outer measure of F symmetric difference is equal to 0. All right, because outer measure of this one is 0 and outer measure of this one will be less than or equal to 0, but it cannot be negative. Therefore, it should be 0. And similarly, outer measure of G difference F is also 0. So consequently, since outer measure of F difference G is 0, F difference G is measurable. Similarly, G difference F is also measurable. So this set is measurable, this set is also measurable. All right. So therefore, you can simplify that F difference G is exactly equal to F difference G. You can write like this one. So this is measurable, and it is given that this is also measurable. So difference of two measurable set is measurable, because just now we have shown that set of collection of measurable set is a sigma algebra. Therefore, this difference will be also a measurable set, and that is exactly equal to this one, F intersection G is measurable. So we know that G can be written in this form, F intersection G union G difference F. So we can write G in this form. So F is measurable, and then G difference F is also measurable, hence G is measurable. All right, G is measurable. So since F intersection G is measurable and this one is measurable, so union of two measurable set is measurable, so G is measurable. All right, so next, this is all about the countable additive. From sub-additive it will convert to additive if the sequence is a disjoint sequence of measurable set. So this is important also. If EI is any sequence of disjoint measurable set, then instead of less than equal to, this will be exactly equal to. If this is sequence of disjoint measurable set, then M star union is exactly equal to sum of the measure. Okay, so that means M star is countably additive in case of disjoint measurable set. All right, so let us prove it. By countable subadditive of M star, we have this one. By countable subadditive, we have this inequality. All right, we also know that this one we have already explained. We also know that M star A is greater than or equal to M star A intersection E1 plus summation I running from 2 to infinity M star A intersection EI intersection union J is less than I is a complement plus M star A intersection union J running from 1 to infinity is a and its complement for any set A. So if you take A is equal to union, all right, in particular if you take A is equal to this union, so you have this one. Why? Because if you take A is equal to union EI, then A intersection E1 will be E1 because they are disjoint. So this will be E1, and here also this will be EI. Alright. So when I is equal to 2, this will be EI, I is equal to 3, this will be E3, like that. Okay. But if you take A is equal to union EI, then you take the complement here, that is empty set. So outer measure of empty set is 0. Therefore, this only remains. Okay. And but this is summation outer measure EI. Alright. That is why we are writing here. Okay. We have this inequality. So inequality 1 and 2 combining, you get exactly equality. So in case of disjoint sequence of set, outer measure of their union is equal to sum of the outer measure of the individual set. So, and this is true also for finite union. This is true also for finite disjoint union. All right. From for each measurable set E, we have outer measure E is equal to measure E. So if E is a measurable set, we will drop this star. Okay. And simply we write ME. Okay. So and we call M as Lebesgue measure. M is called Lebesgue measure. Right. So and then we can define measure in abstract way like this. We can define the measure M to be an extended real valued set function defined on the sigma algebra M or measurable set such that measure of phi is equal to 0 and measure of disjoint union is equal to sum of the measure for each disjoint sequence of union of sets in M. Alright. So every interval is measurable. Lastly, let us prove that every interval is measurable. So this is also one of the important one. So case 1, suppose the interval is in this form, infinite interval closed on the left side A infinity. So for any set A, we wish to show that M star A greater than or equal to M star A intersection, that is complement of this one is minus infinity A, and M star A intersection this set itself. So we want to show this inequality. Alright. So then we can write A1 is equal to A intersection minus infinity A. This is, you can write A1, and this one you can write A2 like this. Then 1 becomes M star A should be greater or equal to M star A1 plus M star A2. Alright. So for a given epsilon, there exists a cover IN of A by intervals such that this is coming directly from the definition of infimum. Alright. So then you can write IN is equal to IN intersection R, because IN is a subset of R. You can write like this, and but R you can write in this form minus infinity A union A close and infinity. Alright. So you can break up the union, then IN intersection this union, IN intersection this one, and that you can write IN prime. This much you can write IN prime, and the second one you can write IN double prime like this. And this is a disjoint union of intervals. Okay. So then IN prime is equal to this, IN double prime is equal to this, and since they are disjoint, length of the interval IN is exactly equal to length of the interval IN prime plus length of the interval IN double prime. So that is true. And since cover IN is a cover, their union should be superset of A. So therefore A intersection this one will be a subset of union N going from 1 to infinity IN intersection this one. But this is, you can simplify like this, union N going from 1 to infinity IN prime, that is A1 is a subset of this one. Therefore, so A intersection A infinity, it is also subset of this union, and that is exactly equal to union IN double prime. So A2 is also subset of IN double prime. So it follows that M star A1, this one is subset of this one, M star A1 will be a subset of it will be less than equal to summation N going from 1 to infinity length of the interval this one. So similarly you can write like this. Okay. So then summing up the two inequality, you will get M star A1 plus M star A2 will be less than equal to this one, and that is exactly equal to length of the interval. Alright. So using 3 we get this one, M star A1 plus M star A2 will be less than equal to M star A plus epsilon for every epsilon. So then you can drop the epsilon, you will get M star A1 plus M star A2 is less than equal to M star A. So it follows that this is exactly equal to this one. Therefore, this interval is measurable. Hence, the interval of this form are measurable. And they are measurable means they are in the collection M, and this is sigma algebra. If this one is here, its complement will be here. Alright. So case number 2, I is equal to minus infinity a. If the interval is of this form, since we have already just shown that this is here, therefore its complement. What is the complement of this one? And that is minus infinity a. So that will be also in M. So therefore it is in M means this set is measurable. Okay. Suppose the interval is in this form, I is equal to minus infinity a here. So we know that minus infinity a can be written as a countable intersection of interval minus infinity a plus 1 upon n. Right? But its member of this intersection is in M, therefore that intersection will be also in M. So a countable intersection of members in M, therefore this set will be in M. Alright. Case number 4. Suppose interval is infinite open interval like this. Since we have already just shown that minus infinity a is in M, therefore the complement of this one, that is a infinity, will be also in M. Alright. So therefore this one will be here. Alright. So case number 4. Suppose I is a finite closed interval or it is finite open interval. So a, b are finite, a is less than b. So in that situation, let us see. We know that a, b closed interval you can write in this form, intersection of these two interval. Alright. But these two interval we have already shown they are in M. Their intersection will be also in M. That means this is in M means this set is measurable. So similarly, you can write this one in this form. So therefore, these are measurable means this is also measurable. That means this is in M. Alright. So this completes. Therefore, this interval are also in M. So this completes the proof. Hence, all intervals are measurable. Alright.